Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. Now we are happy to announce that Unacademy is going to handling the GATE and engineering service subjects to provide a better quality information to the students. About myself, I G Venkatrao. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examination. At present, I am pursuing PhD from JNTU Kakinada. My specialization is VLSI. First, we check how to get the Unacademy Learning app into your device. If it is available in your device, it's okay. Otherwise, immediately install it. Just go to Play Store, type Unacademy. After typing Unacademy, you get the Unacademy Learning app like this. You get Unacademy Learning app like this. Now, click on the install button here. Once you click on this install button, it will install the Unacademy Learning app into your device. Okay, and after that, once you open that Unacademy Learning app, you get what are the different courses available in that and what are the top educators handling the subjects in that course. Okay, and brief introduction about that educators also. Okay, it is very helpful to the students. They can assess which type of faculty are taking our classes. Okay, and here I am going to showing some of the top educators who are taking the classes in Unacademy. Tiwari sir, Goyal sir, Jaspal Singh sir and Jain sir. And here few more faculty. Okay, now I am happy to announce that now we are going to start two new batches for GATE, one for GATE 2023 and another one is for GATE 2022 for different disciplines. Okay, there is a Ascent batch for GATE 2023 for mechanical engineering. This is going to start from 8th February. And again, there is a Evolve batch for GATE 2022. This is also for mechanical engineering students who are awaiting the GATE for the next coming year. This batch is starting from 8th February. Here are the top educators who are handling these subjects in that. Next, there is a Ascent batch for GATE 2023 for civil engineering. Okay, now this batch is starting from 8th February. Here are the top faculty who are taking the classes for this civil engineering. And again, there is a Evolve batch for GATE 2022 for civil engineering itself. This is going to start from 8th February. Next, there is a Evolve batch for GATE 2022. Here are the top faculty who are handling the subjects of computer science and information technology. This batch starting from 8th February 2021. And next, there is a Ascend batch for GATE 2023. This batch is going to start from 1st February, already started for electrical engineering. This is here you observe that more number of faculty for electrical engineering because more number of subjects are there for electrical students. Now, for electronics and communication, there is a Ascent batch for GATE 2023. Here are the top faculty who are handling the classes here, and this batch is going to start from 1st February. And there is a Evolve batch for GATE 2022 for electrical engineering. Again, this batch is going to start from 1st February. And there is a Evolve batch for electronics and communication that started from 1st February. Next, there is a Evolve batch for GATE 2022 for chemical engineering. Okay, chemical engineering. For this is started from 25th of January 2021. Now, just these are the different disciplines available in Unacademy for GATE and engineering service students. Electronics, communication engineering, mechanical, electrical, computer science and IT department, civil engineering, instrumentation, production and industrial, and next one is a chemical engineering. Okay, now here we have two subscriptions we are providing to the students. One is a plus subscription. Plus subscription is the basic subscription, and next one level is the iconic subscription. It is the next level of the basic. Here we provide a personal coach to you. Okay, the importance of personal coach is he is going to handle whatever the things you need for getting a success in your examinations, all those work is taken care by that personal coach. He will guide you continuously during your preparation time, during your class time. Mostly the main function of this one is his personal coach is, after completion of writing every exam from your side, we will prepare a analyze report on that exam. From that, where you are strong, where you need more preparation, where you are committing mistakes, everything is written by personal coach. And based on that, they will prepare proper study planner to you, especially for each and every student who are joining Iconic batch. Okay, for them, by following that study plan and whatever the material provided to you, by following these two properly, definitely you will get success in your examinations. That is the motive here, to provide a personal coach to you. Okay, so if you observe the price of it, now the price for Iconic batch is hardly the amount what you are paying at outside institutions, and price for plus subscription is the price what you are spending for transportation to move from your home to the place where you are taking the coaching for this gate. Okay, so very nominal prices they are charging, and the beauty here is they are providing EMI option also. See, for plus subscription, 1 month subscription, 3 months, 6 months, 1 year. Okay, like that, different subscriptions are there. For 1 year, if you observe, it is 30,250 rupees. Okay, and by using my code VROW10 during subscription, you get 10% discount. After getting 10% discount, it became 27,225 rupees only. This is close to the just 1 or 2,000 more than the amount what you have to spend for transportation purpose throughout the year to take the to attend the classes somewhere out of away from your home. Okay, now next we are going to Iconic plan. Here only two subscriptions are there, 12-month subscription and 24-month subscription. For 12-month subscription, the cost is 50,250 rupees. After getting 10% discount, it became 45,225 rupees. So during this subscription, don't forget to use my code VROW10 to get 10% discount. So my dear students, whatever thing is happening at outside, your learning process should continue. Why I am saying this one is, we know the situation since last year what happened. Okay, since March what happened. Okay, so but whatever thing is happened outside, but your learning process should be continue, cannot stop. So don't waste your time. Okay, join as early as possible and get more benefits. Thank you. Now we are going to our topic. So now today's topic is calculation of contact potential at PN junction, and after that calculation of electric field depletion region in a biased PN junction. Okay, in a biased PN junction. Fine. First I am going to calculating the contact potential. So these are the topics already we completed. And we derived depletion region width also here. So the equation for depletion region width what we derived is square root of 2 epsilon by q into 1 by NA plus 1 by ND into V naught, contact potential V naught. Okay, now so in this equation we know every value, we know the epsilon value, q value, Na, Nd, but except V naught we know everything. So that's why first I am going to derive the equation for contact potential V naught. Okay, now equation for contact potential. equation for contact potential. Contact potential. Equation for contact potential. See, what are the PN junction we have under steady state open circuit condition? Here is the depletion region on P side. Here is the depletion region extension on N side. Here a negative immobile ions are there. Here a positive immobile ions are present. Now, your PN junction diode is under open circuit condition. So the current flowing through your junction is 0. Current flowing through the PN junction is 0. Now, once current is 0, you can write current density also 0. Now the total current density is we can write it as J drift, current density by electrons plus current density by holes. Now, current density by electrons is two things here, drift current and diffusion current. Similarly for this one also, drift current and diffusion current. Now, this one is also 0, this one also 0. No current due to electrons and no current due to holes. Now, I am going to taking this part. Therefore, whole current density is 0. In this whole current density, we have two parts. J drift by hole plus J diffusion by hole. Sum of these two is equals to 0. Okay. Now, I am concentrating on this equation. So we know the equation for J drift. So J drift is by hole is, we know that P into Q into mu P into electric field. Next, J diffusion by hole is minus dP into Q into dP by dx. So sum of these two equals to 0. Now that's what I am going to doing here. Therefore, P into Q into mu P into E plus this one. So it is minus dP into Q into dP by dx equals to 0. Now taking this one this side, therefore P into Q into mu P into whatever the electric field here we have, I am taking that electric field is minus dV by dx. That is the equation for electric field. Okay, so it is minus dV by dx equals to dP into Q into dP by dx. Now Q gets cancelled and dx also gets cancelled. Just to simplify this, therefore P into mu P minus P into mu P into dV equals to dP into dP, small dP. Now I am taking this mu P this side. Whatever the mu P here you have, I am taking this one this side. And I am taking this P also this side. Now I am writing this is 1 by P. So now this is the equation we have. So minus dV. So I am taking this negative also this side. So dV is dP by mu P into dP, 1 by P into dP. So therefore dV is minus dP by mu P is nothing but a Vt, that is Einstein relation, into 1 by P into dP. Now I am taking integration on both sides. Okay. So now our equation is, see this, integral dv equals to my integral minus vt into 1 by p into dp. This is our equation. Okay, so here a net negative charge is present. We are representing that negative charge by Vp naught, and here positive charge by Vn naught. So this depletion region extension here is, and one more. So here dV, that's why I taken limits Vp naught, Vn naught. Okay, Vp naught to Vn naught. And already we defined Vn naught minus Vp naught is the V naught contact potential. Next, here dP is there. Now limits should be in terms of hole concentration. Now in P region, hole concentration is Pp. In N region, hole concentration is Pn. Okay, because here hole concentration is Pp, which is approximately Na. In this region, Pn is approximately Ni square by Nd. So I'm taking that limits Pp, Pn. Because here you taken P to N. Similarly, P to N I am taking. Now just simplify that. So integral dv is V. Limits are Vp naught to Vn naught equals to minus Vt into integral 1 by x dx. It is ln of x. So ln of p. Limits are pp to pn. So this is Vn naught minus Vp naught, Vn naught minus Vp naught equals to, so which is equals to contact potential V naught. Already we defined it. We are calling it as contact potential V naught, which is minus Vt into ln of Pn minus ln of Pp. Therefore, V naught is Vt into ln of Pp, taking minus into this, minus ln of Pn. So log A minus log B, we can write it as log A by B. So therefore, V naught equals to Vt into ln of Pp by Pn. Pp is whole concentration in a P region. So whole concentration in a P region, we can write Pp is approximately amount of doping Na in P region, and Pn is electron whole concentration in a N region. So that is Ni square by Nd according to mass action law. Take these two, substitute here. Therefore V naught is Vt into ln of Na into Nd by Ni square. Na into Nd by Ni square. This is the equation for contact potential. V naught is Vt into ln of Na into Nd by Ni square. Okay, and so from this equation, whatever the equation here we have V naught. From this equation, I am going to writing, taking Vt this side, then it became V naught by Vt. Vt is volt equivalent of temperature, so we know that its value is 26 millivolts at room temperature, equals to ln of Pp by Pn. Now from this we can write Pp is Pn into e power V naught by Vt. This is called law of junction. Law of junction. Law of junction. Okay. sometimes they will ask, see, and one more thing, this is the case for when two in a semiconductor, half side doped with p-type impurity, other side doped with n-type impurity. That is the case. Now for example, my semiconductor is like this, this is the semiconductor I have. Let us take it as p-type semiconductor. Here doping is p1, doping profile. Here doping profile is p2. So due to change in doping profile, at this end doping is p1, heavily lightly doped. At this end it is heavily doped. Okay. So due to this, an electric field is directed and developed in this. Okay. So due to that, the potential developed within this can be calculated from this. Now we can write simply P1 is equals to P2 into e power V naught, whatever the potential developed here, V by Vt. So you know the P1, P2 and Vt. Okay, from that you get the potential built in this. So for example, if you take some example, now let us, in a semiconductor, hole distribution is given like this. This is a semiconductor, hole distribution is given like this. So it is P1, it is P2. Just by substituting these P1, P2 values, whatever the voltage builder developed within that material, you can easily calculate in that. Okay, so you can apply this one to either single semiconductor with different doping profiles or a p-n junction diode. Okay, so generally we call it as a law of junction. This is the way of calculating the contact potential. So far we know the contact potential equation. V naught is Vt into Ln of Na Nd by Ni square. That is the equation for contact potential. Next. So far whatever the equations we derived, I am going to writing all the equations at one point. See, first we represented the, so these are the formulas what we derived so far, or equations. First we have volume charge density. It is minus Na into Q or Nd into Q or 0. This is from minus xp naught to 0, and this is from 0 to x n naught, and this is elsewhere. And based on, by using this, we derived an equation for electric field, which is minus Na into Q by epsilon into xp naught. Under open circuit condition it is into 1 plus x by xp naught, or minus Nd into Q by epsilon into xn naught. So it is into 1 minus x by xn naught, or it is 0. It is 0. So this is the case for x value in between minus xp naught to 0, and this is the case for 0 to xn naught, and this is elsewhere. You can take anywhere. So this is the equation for electric fields, and after that, in the same equation, from the same equation we calculated the maximum electric field, E naught, maximum electric field. This is a maximum value of electric field, that is minus Na into Q by epsilon into xp naught, or minus Nd into Q by epsilon into xn naught, any one of this. By equating these two, we get By equating those two, we get one equation, one relation in between xp naught and xn naught. That is Na into, this is the third set, Na into xp naught equals to Nd into xn naught. And we know at the same time, we know this depletion region with W naught is xp naught plus xn naught. This is the basic equation. From the knowledge of these two, we derived extension of depletion region in P side as well as extension of depletion region on N side. So xp naught depletion, extension of depletion region in P side is W naught into Nd by Na plus Nd, and xn naught is W naught into Na by Na plus Nd. Na plus Nd. These are the equations of xp naught and xn naught, and W naught is the unknown parameter, and we derived an equation for that one also. W naught is square root of 2 epsilon by q into 1 by Na plus 1 by Nd into contact potential V naught. And the equation for contact potential just before we derived, it is V naught equals to Vt into ln of Na into Nd by Ni square, Na into Nd by Ni square. Okay, so these are the equations so far we derived. And you observed or not, all these equations are for a open circuited PN junction diode. Okay. Now if diode is biased under biasing condition, then what happens? Now we go and check it. Now see, let us, I am taking PN junction diode. P region and N region. Okay, already at junction you have a contact potential, developed contact potential V naught is there. Okay, so this is acts as a barrier between P region and N region. Okay, now a negative immobile ions here, a positive immobile ions takes place here. Once you applied some voltage across these two terminals, some voltage V you are applying, let us take some voltage V you are going to be applying. In that case, initially the barrier, across this barrier the voltage is V naught only, barrier voltage we called it. Now once you biased this with voltage V, it may be forward bias or reverse bias, whatever it is. Once you bias voltage V, then V barrier, there is a voltage, we call it V barrier, barrier voltage is equals to V naught minus whatever the applied voltage, V applied. So this is the applied voltage, V applied. Okay, V applied, that is the barrier voltage. Now, for example, diode is in reverse bias. In reverse bias, V applied is equals to minus VR, because you are going to be applying this. Now in reverse bias, this is the case, PN junction diode connected to negative, PN connected to positive. So this is the VR. So applied is minus VR. Therefore V barrier is written as V naught minus of minus VR. So it became V0 plus VR. Okay. We also called it junction voltage. V0 plus VR also called as junction voltage. Okay. For example, diode is in forward bias. Now in forward bias, this is the case. PN junction, P connected to positive and N connected to negative. Okay, P connected to positive, N connected to negative. This is VD, let us applied voltage, DVD, forward voltage. Okay, now we can write this. Now V barrier became V0 minus V applied. So the applied voltage here is VD or VF. Okay, VD or VF, V0 minus VF. Okay, now you can write under biasing conditions, the contact potential, the depletion region width W0 is square root of, sorry, now no need of subscript O because under biasing we are writing it as a W. Depletion width, depletion region under biasing conditions. Under biasing condition. Biasing condition. See, it is a 2 epsilon by Q. 2 epsilon by Q into 1 by Na plus 1 by Nd into V barrier. That's it. V barrier. Okay, under reverse bias, see this. In reverse bias, what happens? In reverse bias, W is square root of this part into, see, this portion as usual into, this is V barrier. We know the value of V barrier under reverse bias, V0 plus VR. So from this what we observed, in reverse voltage its value is more, it is increasing, that's why width is increasing. So in reverse bias, depletion width is greater than W0. Under open circuit condition, whatever the depletion region width you have, compared to that, under reverse biasing condition, the depletion width is more because of this value. Okay. Similarly, if you check in forward bias, so you can write a depletion width is square root of 2 epsilon by Q into 1 by Na plus 1 by Nd into same V barrier, but V barrier value is here V0 minus Vd applied voltage. Okay, now see this. So now here width is W exists for Vd less than V0. Okay, if V0 is, sorry, if Vd applied voltage, Vd is greater than or equals to V0, now depletion width is 0. There is no depletion region width. Okay, so because of this, once Vd is increasing, okay, Vd is increasing, the depletion width is going to be decreasing. So in forward bias, whatever the depletion region width taking place at the junction, the depletion width is less than the under open circuit condition, whatever the depletion region width we have. You may ask one thing, sir, in forward bias you are discussing about depletion region width. Yes, I am discussing about depletion region width in forward bias itself. Because if this is the case, if applied voltage VD is less than contact potential, in that case depletion width is existing. See, under open circuit conditions this is the case. This is the depletion region width under open circuit condition. When you bias this one, when it is forward bias, okay, then charge carriers are entering into this. Now the depletion width is going to be decreasing. Now this is the only depletion region. So the width of depletion region is decreasing. Whenever the applied forward voltage is greater than or equals to contact potential V0 we have, that means V gamma, threshold voltage we called it in general, greater than or equals to that, then the depletion, now at this point all charge carriers are crossing freely through the junction. Now there is no space which is covered by only immobile ions, then we can take depletion width is 0, but don't take exactly 0, approximately 0, close to 0. So we are not considering the depletion region width in forward bias if the applied forward voltage is greater than or equals to contact potential. Okay, if it is less than, it should exist. Okay, anyway, once your diode is under reverse bias, once a diode is in biasing, depletion width is W. Okay, once a diode is under bias, depletion width is W. Now I am going to writing the whatever the expression so far we derived. Electric field, okay, extension of depletion region on P side, extension of depletion region on N side, okay, and all these things I am going to be representing for a biased diode. Now for a biased diode, depletion region width is W. Let us take W. I am not taking W not, sir, it is W. Okay, W. And here condition is in forward bias, applied voltage VD is less than V0, then only it is going to be exist. Okay, now you can apply this one to in the forward bias or reverse bias. In forward bias, what is the equation? Already we derived just in a before slide. And what is the equation for width in reverse bias? Already we defined that one in previous slide. Now your electric field is, our general equation is minus NA into Q by epsilon into XP naught into 1 plus X by XP naught. This is the expression we have. Just to do one thing, just to remove this subscript O, because your diode is under bias, not open circuit. Okay, and at the same time another equation we have minus ND into Q by epsilon into Xn into 1 minus X by Xn. Now you may ask one thing, sir, what are the values of XP and Xn? We don't know the values of that. We know only XP naught and Xn naught. Under open circuit conditions only we know the values of that. See, sir, you know the values of XP and Xn also. See this. Your equation for XP naught is W naught into ND by NA plus ND. Okay, as well as Xn naught is W naught into NA by NA plus ND. So once you know this, so from this you get the XP and Xn value. Simple. Just to remove the subscript here. O here also. So this is the depletion region width under biased diode. In a biased diode, depletion region width is W. Okay, from that you get the XP and XN, extension of depletion region in P side in a biased diode, extension of depletion region in N side in a biased diode. Now electric field E. Okay, so these are the different equations which are useful to you while solving the problems. Okay, sir? Is it okay? Just a simple thing. Initially we have open circuit, and one more, there is no change in contact potential. Don't change the equation of contact potential. Equation for contact potential is same. V naught is Vt into ln of Na into Nd by Ni square. Okay, so when two different dissimilar materials are in contact, at that contact some potential is going to be developed. Now you may ask one thing, sir, if I take a PN junction diode, okay, in that junction diode also, can I get some potential value, contact potential value? You can get it. See, this is our PN junction, P region and N region. Here some depletion region. Now some potential is, this potential is developed across this. You can get it, but practically, if you are checking that in a multimeter, you are not getting anything. Why? Because here you are using one conducting lead, here we are using conducting lead, another conducting lead. Okay, now this is edge is a metal coating edge, this edge also a metal coating or heavily doped N type. See, this is the general way of placing your PN junction diode. See, here either they take this is a total metal or a heavily doped p-type semiconductor, and here heavily doped n-type semiconductor. This is heavily doped and lightly doped, so different dissimilar materials. And this is a metal, this is p-type, different materials. Some contact potential also develop here, some contact potential also develop here. Okay, now if you apply KVL to this, the net value is 0. That's why in voltmeter we are unable to get that value. Okay, that is the reason. So today's session we covered contact potential value we derived, that is Vt equal to V naught equal to Vt into ln of Na Nd by Ni square. Okay, and after that we represented what are the parameters related to a PN junction diode. All the parameters we represented for a bias junction also. Under open circuit, subscript O we added, without subscript means it is under bias. Okay, only W value is changing for forward bias and reverse bias, remaining all are same. Okay, so now I'm closing this session, sir. Next session we go to the next topic. Thank you, sir. Thanks to one and all. Thanks for your spending your valuable time with us. Okay, and don't forget to use my code VRAW10 during subscription to get 10% of discount, and hit the bell symbol, bell icon for getting the notifications. Subscribe, don't forget to subscribe, and join our Telegram group to get updates, latest updates on our upcoming videos. And please give your valuable comments on our sessions to strengthen ourselves and to provide a better quality information to upcoming students. Thank you, sir. Thank you very much. Thanks for spending your valuable time with us. And once again, I am welcoming you all to Unacademy. Unacademy is the India's largest online learning platform. Thank you. Thank you very much.